We can talk after class and figure something out. Okay, so for those of you asking about the homework question on, what is it, 8F, on, was it an exothermic reaction or endothermic? So we wanted an exothermic reaction. We wanted to label the axes. We wanted to label the reactants and products. We wanted to label what's called the activation energy, which quite often I will abbreviate AE in the future. And then the last one was the heat released, right? In this case, because it's exothermic, it would be heat released. So there's one for the endothermic reaction and for the exothermic reaction on page 159 and 160. And it's in Chapter 8, notice. And we first encountered this in Chapter 4. So this is kind of a review of Chapter 4, but they're adding one new piece of information in there. And that's the concept of of the change in the amount of energy, which we kind of mentioned in Chapter 4. And then they're also adding in that activation energy. So this is something I didn't cover in lecture, so forgot in lecture. But this is why you have a book. That way when Jay gets senile and old, you guys can occasionally read the book or look at it. Plus, it's also good for a second look at it. How many people have looked at Chapter 8 in the book? So, here's our axes. And of course, we've got our X and our Y. And on this axis, what we're considering is our reaction progress. So this is kind of like a time axis, meaning at the beginning of the reaction, we have just our reactants in the reaction, right? And they have some energy level, so we're going to plot energy on the left axis. And we can call it potential energy if we want, since it's technically the energy stored in those chemical bonds. Good morning, Jess. That's now 2 in a row. So then in an exothermic reaction, the energy of the products is lower in energy, right? So we know at some later time in the reaction, our products are going to be over here. And in between is sort of, you know, it doesn't really have a physical locale. I mean, reactions occur over time. But, you know, this is sort of an abstraction. But the idea is that you need a bit of energy input into the system. So this amount of energy, this little hump, is what we call our activation energy. And it's basically the energy required to start a reaction. Oops. Energy required to start a reaction. You can think about it kind of like a match. The match won't burn until you strike it, right? Or you can't light a candle until you bring the match to the candle, meaning the candle just doesn't spontaneously burst into flame, right? That reaction doesn't happen immediately. Same thing for like most combustion reactions. You don't just burn something instantaneously, you have to give it a little spark to ignite it to get it going. That's what the activation energy represents. And then the difference in energy between the reactants and the products, this is the amount of energy change in the reaction. And since this is an exothermic reaction, it represents the energy released. Which is why if we write a reaction, and we'll keep it nice and simple, we won't even say what's reacting, we put the energy term, or we've been using the word heat sometimes, on the right-hand side of a reaction for an exothermic. And if you want to see what an endothermic graph looks like, it's very similar. It's just that the energy between the reactants and the products is changed, meaning the reactants are now lower in energy and the products are higher in energy, and the energy goes as a reactant instead of a product. And it slightly changes what we consider the activation energy and the energy change in the reaction. But that's on page 159, 160. In this class, what we'll mostly use this for is later on in the biochemistry chapter when we talk about enzymes. Do you guys know what an enzyme is? So enzymes are compounds that speed up chemical reactions in the body, or biological reactions is kind of how I usually label them. Exactly. They lower the activation energy by changing the pathway that the reaction occurs. We'll spend an entire chapter, basically we'll spend an entire chapter talking about how enzymes function in a vague sense. I mean, you got to realize you could have an entire course on just enzyme activity. And so, we'll cover a broad overview. You'll probably actually end up, if you take Bio 111, 112, I think Todd covers enzymes actually more than we do, and Sarah covers it a little more in depth. We approach it in a very abstract way. But we also look at it maybe slightly differently in this idea of activation energy, or in terms of that, or finding an alternative pathway to complete. So, if you want points back on the homework for me taking off points for not reading the book, let me know and I will put those. I've already got a small list here. So, what I want to talk about in Chapter 9 is just a quick review, in that we handed you a chart that sort of had a bunch of boxes like this, and I consider that the flow chart or a map for Chapter 9, meaning if you can understand that chart, if you can write that on a piece of paper, fill in the blanks, and then use that as a roadmap, it's kind of like you can't get lost. I mean, you might occasionally take a left turn when you were supposed to take a right, but for the most part with that map, I think you'll be pretty good. And so the first set of problems we looked at, and then also in homework 9B, was just mole A to mole B. So looking at that mole to mole ratio. And so that's sort of our middle point, we said, for all reactions. And the reason we have to do things in terms of moles is because everything weighs a different mass, so you can't compare masses between reactants and products. Instead, you have to compare numbers of atoms, right? And what does a mole really represent? It's really just 6.02 times 10 to the 23 atoms. And so that mole-to-mole ratio really is simply just a large number of atoms react with another large number of atoms, and it tells us the ratio of those atoms or molecules that have to react. And then we added on another part. We said, well, we already know from Chapter 7 if I have grams of A, I can convert to moles of A. And so this was our molecular weight from Chapter 7. And that's a unique constant, remember, in that it's different for every single compound. And so here, this depends on the compound. And, again, we can do the exact same thing on the opposite side. And here again, this is molecular weight, Chapter 7, and it depends on the compound. And of course, the mole-to-mole ratio depends on the balanced reaction. And so basically for every single question in Chapter 9, we have to have a balanced reaction, and for a lot of the problems we need to make sure that we also have all the molecular weights calculated. As a reminder on the homework, there's a molecular weight calculator on the website. But the key here is don't forget how to calculate molecular weights, because on the test you don't get that molecular weight calculator. So it's supposed to speed up doing things on the homework by removing one of the tedious parts, which is simply calculating molecular weights. But I also don't want you to forget it, so on the test, you don't get a molecular weight calculator. You just get your regular calculator in a periodic table. So that's the Chapter 9 flowchart. And so what we're going to be doing today almost exclusively is going from one end of the chart to the other in different ways. And what we have to really focus on is how we interpret those different ways. So like we started with on Monday, realize that everything we talk about, we can make an analogy to baking cookies, or baking anything for that matter, because a chemical equation is really just a chemical recipe. And so if you can understand it in terms of baking, and then translate that to using the funky grams per mole, molecular weights, and mole-to-mole ratios in chemistry, then I think you'll be okay. And if you ever get stuck in chemistry, simply write cookies and sugar and flour above things and ask yourself what you do in a recipe, and then do that with your chemistry stuff. So we're going to have another recipe. I've got 2 cups sugar plus 3 cups flour, and I'm going to make 10 cookies. Now, if you remember from the previous homework, what we did is we'd just say something like, you've got 5 cups of sugar, how many cookies can you make? Or you want to make 60 cookies, how many cups of sugar you can make? We are going from one value to another. Questions now are going to be like, for instance, I have 7.5 cups sugar and 10 cups flour. And then we're going to ask things like, A, what's the limiting reactant? Now, what we mean by limiting reactant is really what you run out of. So it's kind of like, for instance, if you go buy hot dogs, you get, what, like 8 hot dogs and 10 buns. You're always running out of hot dogs before buns. Or when's the last time you went to the store, bought chips and salsa, and didn't run out of one or the other first? I mean, I always either run out of chips and have to go buy more chips, or I run out of salsa and have to go buy more salsa. Same thing in a chemical reaction. Every time you're doing a chemical reaction, unless you get lucky and you have exactly the right amount of both reactants, you're going to run out of one of them. So what we're going to ask ourselves is which one we run out of first. We can ask questions like, how many cookies do I make? We can ask, how much of the excess reagent is left over? We can ask, what is my percent yield? And I'll define these terms as we're going along. What is the percent yield of cookies? So the idea behind these 4 questions, just a second.
I didn't even know which word.
Oh, which word are you looking at?
I have to access.
Reagent or reactant. The words are interchangeable. If you can answer these 4 questions, this is the test question on the test, meaning there will be at least one question that simply says, for a chemical reaction, can you answer those 4 parts? So let's work on each of those parts. So part A is looking at the limiting reactant. Yes, I will go back. Dude, where's my cookies?
I didn't have cookies
I know, you eat healthy. I want cookies.
either.
Good to go, Jess, or waiting?
It's time to be up so early.
Oh, I know. I always have to have breakfast in the morning. I get cranky. I get cranky.
What a nice evening.
I know.
I like breaking things.
The team that, brings food to each other wins. I don't know. Maybe. So for the limiting reactant, what we want to do is we want to find out basically what we run out of. There's 2 ways to do this. The first way is arguably the easiest, meaning the shortest amount of math. It's also the easiest to screw up, so I'm not going to show you how to do it. If you want to read the book and learn how to do that way, go ahead. If you have it in your mind that you can do it a different way, that's probably the way I'm talking about. I'm going to show you the second way. It's a little bit more work, but it's easier to screw up, or it's less hard. It's less likely to screw up, and the way I'm going to show you also answers question B, which inevitably is the second question. So really you're going to do twice as much work, but you also get 2 answers. Whereas if you do the other way, you get just answer A and you still have to go and do answer B. So in the end, the net effect is the same amount of work. So the idea is that I need to take and calculate reactant 1 to product 1, and I need to convert reactant 2 to product 1, meaning the same product. So we have to compare to the same product. Now in this case, I only have one product, cookies, right? But in most chemical reactions, we usually have 2 or more products. And so you just have to pick one of the 2. And we'll, of course, do all of this with a normal chemical reaction, too. And so the idea is we're going to convert from one to the other, and then whichever makes the least P1 is the limiting reactant. And I'm going to abbreviate limiting reactant LR because that's what I do from now on. And that's what we run out of first. So I'm going to take the numbers I had, which were 7.5 cups of sugar, and I'm just going to do a conversion like we were kind of with the, in the chemical reaction, this would be simply like a mole to mole conversion. We know there's 2 cups sugar for, what was it, 10 cookies? Yep. 10 cookies. And I picked nice uneven numbers a little bit just because I didn't want anyone just doing this in your head. So we can make 37.5 cookies. And then I'm going to do the exact same thing for my flour. I said I have 10 cups of flour, and we know that 3 cups of flour gave us 10 cookies too, right? So we've got 100 divided by 3, or this one can make 33.3 cookies.
So I got a question.
Yes.
You can't make 33 cookies.
Well, you can if we're talking about moles, right? Now, if we're talking about an atom, you're right. Now, I have to admit, you really, a third of a cookie is kind of a lame-ass cookie. Well, what I usually make is 36 cookies, and then I have 1.5 that I eat the dough left over. Inevitably, some of the dough gets eaten. Now see, it's a good thing that you bring up burnt cookies because that's part D. Right. So, which one is my limiting reactant? Yeah, the flour. This produces the least amount of cookies. Therefore, I run out of flour first. Therefore, it's what we term our limiting reactant. So in a chemical reaction, the exact same thing is going to happen. We're going to run out of one of the reactants, and the reaction is done at that point. We can't make any more cookies. We can't make any more product. So the answer to part A is then 10 cups of flour. Or technically, I guess it's really just flour. So flour is our limiting reactant. But we've also answered B, notice, because B said, how many cookies do I make? Well, we know we make 33.3 cookies. So most of the problems in my chemistry test are going to be the exact same question. It's going to ask you, what is the limiting reactant? And then the very next question is, how many cookies do you make? Jess?
Could you round it since you can't make a third of a cookie?
We're not going to worry about rounding right now or sig figs at all. Because sig figs in baking don't make as much sense, right? But sig figs in chemistry, then yes, you would round to how many ever sig figs you have in your masses. We'll show you that for chemistry. Right now, we're worrying about baking cookies. So we're happy with that. So we've answered A and B, right? Now C was how much of the excess reactant, and we'll just call that ER from now on, is left over. So technically, to answer this question, we really have to first ask how much we use. Because if you don't know how much sugar you used, you don't know how much is left over, right? Jess?
Could you just go or you subtract 37.5 from 33.3?
No, because that's cookies, right? We want to know about sugar. So the difference in the number of cookies, you could actually use that technically to solve the question, but it's not the easiest way. How about? And really, once you make 33.3 cookies, you're done making cookies, right? And so what we're going to do is we're going to really just say, if I've got reactant 1, I need to convert it to reactant 2. Or really what I'm taking is saying I want to convert my limiting reactant to how much of my excess reactant is used. And so the idea is that I know if I have 10 cups of sugar, 10 cups of flour was my limiting reactant, right? So there's my limiting reactant. and I know that there was 3 cups flour for 2 cups sugar, that's 20 divided by 3. Should be able to do that in my head. 6.7, we'll just round. 6.7 cups of sugar, but that's how much I need, right? Or that's how much I use. And so the idea is that you have to tack on a little bit. We started with what, 7.5 cups? We used 6.7 cups, and so left over, I should be able to do that in my head, 0.8 cups. And so my answer really is that 0.8 cups. So that's the answer to C, actually. So notice that I'm doing the same sorts of things, meaning I'm using that mole-to-mole ratio constantly, right, from the reaction. And it's really mostly a question of what I'm converting to what I'm converting. So there's a couple ways you can learn this. You can, I think, if you can kind of remember or memorize it in these terms and then know how to do the stuff in between, that's a good way to think about it. You know, because one of them is converting reactants to products, the other one is converting a reactant to a reactant, and kind of think about it that way. And then if you focus on that core part, then throwing on the chemistry stuff, which is grams and molecular weights and other things, isn't too bad. And then, like I said, if you get lost, make it sound like a cooking question. Just put cups and sugar and flour in there. It probably will work. Okay, so that's how much is left over. Question D was the last question, which simply said, what is the percent yield? And what we mean by percent yield is basically, in reality, in real life, meaning lab or even the kitchen, kitchen's close enough to being real, you rarely make 100% of the product. In the kitchen, maybe you burnt a few cookies, like if you're Cody. Is it Y or I? Y. Okay.
Cody, you can't cook.
Or in lab, for instance, or maybe you eat some before they actually get to class. You eat some dough, right? Or in lab, you know, you might spill some. You might accidentally throw some away, or you know, throw some away. Yeah, there's lots of ways that things can go wrong, and I actually, in honestly, most reactions don't go to 100%. And so, depending upon the reaction you do and the conditions, the best you might actually be able to do is 90% or something. And so, the way we're going to define percent yield is then that it's the actual yield divided by what we call that theoretical yield. And of course, if it's a percent, we have to multiply everything times 100. So for example, in our baking exercise, our theoretical yield was how much? How many cookies could we make? 33.3 cookies. Now, if we say that in real life, meaning our actual yield, and you almost have to be given the actual yield, was, say, 27 cookies, then the percent yield is simply 27 divided by 33.3 times 100, or? Yes.
And that's the answer to C.
And this is the answer to D, right?
I mean B.
D?
Theoretical yield.
Yeah, this was, oh yeah, this was the answer. This was part B, actually. So see, you get to use all the parts multiple times, too. And so in this case, we got 81% yield. Not bad. We'd take a B for making cookies.
And where'd you get 27 from?
That has to be given generally.
That's like when you actually do it.
Right, so like if you were in lab, that's what you would actually measure. You'd say, I just made a bunch of stuff, how much did I make? And then you ask yourself, how much should I have made? And you calculate your percent yield. On a piece of paper or a test question, it would be something like, you know, you make 25 grams of your product, what's your percent yield? Well, then you have to go and do all the other work to calculate your limiting reactant and your thing. And so really, if you look at it, depending upon the question I ask, you almost always have to calculate a limiting reactant. You almost always have to calculate the theoretical yield in the question, even if you're only answering part C and part D. And so really, any one of those 3 or 4 questions really means you have to do all the rest almost. And so I'm nice, I just make you do all of it. Now, on the internet, there's a bunch of questions, and they'll only ask you to do one of them at a time just because it was easiest. But you have to do all the other steps right to get the answer correct. And so it might simply say, you know, well, here, I'll show you real quick what it would say. Why not just pull it up while people are thinking? So let's see. Here's the website. Why not is because the website's slow all the time and it annoys me. So there's simple conversions, harder conversions, and we haven't gotten to titrations yet. We'll worry about that either Thursday or Friday. Depending on if we have water tomorrow, we may do the titration lab, and if we don't have water tomorrow, we may just lecture and then try to do the lab on Friday. We'll just have to see how things go. Yes. Well, Kramer. I keep saying Rector probably because I've been in Rector for 8 years, so.
We're not supposed to use the water over here? That's
Correct.
what you're saying? Oh, I was like, what in the hell?
So, for instance, you know, this question simply asks, what's the limiting reactant, right? And, you know, you can, of course, check your answer. And then this question, for instance, asks you how much excess reagent. So to figure out your excess reagent, you really actually have to figure out your limiting reagent. You actually get, at the same time, your percent or your theoretical yield, right? And now you have to do that extra step where you figure out how much you use and stuff. So, you know, the questions here on the internet will only ask you one of those things, but you have to calculate a bunch of them. What I recommend when you do this, if you want to practice these, write down the question verbatim, and then go ahead and answer it. And then if this thing tells you it's wrong, take a look at your answer. For instance, if you typed 8.62, you probably got it right. You were doing the right thing, right? You just missed the sig fig part. Because the computer is very literal. It's going to say, do it exactly this way. Or, you know, if you end up coming and, you know, you get the wrong answer and you're not sure why you got the wrong answer, unless you have the question written down and what the computer said the answer is, I can't tell if it's something that I programmed wrong in the computer or something that you did wrong on the calculation. So make sure, if you're going to do these and then want to ask me questions about it, that you write down everything from the question.
Is there paper extra practice?
No, but I got to be honest, I could arguably just hit the button and copy paste them onto the piece of paper.
That'd be great.
I mean, I think it's just as easy to push the thing. We'll
I
see.
hate doing chemistry on the computer. It's the reason it drives me crazy.
We'll see if I can do it. Okay.
Okay.
Boy, that was really an easy one. Oh, that's just molecular weight. I was clicking. And then, like, simple conversions are the ones where we're just asking, we're taking one product. You don't have to do limiting reactant steps usually. So there's a variety of questions that you can practice. And really, if you can do these 3 sets, that's pretty much how I generate the test. I just go and be like, okay, test question. Bam, there it is. Don't even have to do any work on my part. It's wonderful. It took me forever to program it, but it's still wonderful. So go ahead and use those. Now, that's A, B, C, and D, right? Does everyone feel like they got a good grasp of the theory? Because I got to be honest, you know, like we took a half hour, and really this is where I think the key is. I took a half hour, and we talked some other stuff, but we really want to fix the theory in your head, because just doing it with chemistry, where I used to start it out that way, some people got it really easy and some people didn't, but I find that if we do it this way and you've got that theoretical background, that if you can relate it to something you're good at and you know how to do already, then hopefully it's better. And for some reason, girls are better at this section than guys. Just kidding. I'm pretty sure I'm the best baker. I'm pretty sure I'm the best baker in this class.
How you know that? How
Most-
you know what I do at home?
You want to have a bake-off? I mean, I'll challenge you to a bake-off. I'm not going to challenge you to a basketball game, just like I don't challenge Jess to go rope steers and jump off running horses and tie goats up. Or I'm probably not going to play volleyball with Brittany. Oh, by the way, how did donkey basketball
Yes, how
go?
did that go?
My team lost in overtime the first game.
Oh,
So upsetting.
Did you score?
Yeah, I scored.
I mean,
I had 2 points. But high lead donkey basketball was like 4 points. That's a solid win in donkey basketball.
okay.
What is it called? I've never heard of it either, but apparently it's not that rare. It's like, oh yeah, we do that all the time.
Yeah, I don't know. Okay, so let's take a look at an example. So we're given the following reaction. SF4 plus H2O goes to make SO2 plus HF. And technically, I guess we should put in some states just to be good practice. And this is usually aqueous. And my question is going to be, given that we have 50.0 grams of SF4 and 100.0 grams of H2O, calculate A, the limiting reactant. Does this look familiar? B, the grams of SO2, let me check. Oh, I didn't even do, yeah, grams of SO2 produced. The amount, or grams of excess reactant left over. And D, the percent yield if in lab, oops, that's backwards. If in lab you made 18.0 grams of SO2. And since I'm making this up, I'll probably, hopefully someone writes this down really nice and well so we can do it. Now see, here's also where chemistry gets tough. For instance, notice, is this reaction balanced? One of the things that we have to be aware of is that, you know, even though I've got A, B, C, and D are my questions, you actually have to start off by balancing the reaction. I'm not going to change the page. I'm just going to balance the reaction. So I've got 1 sulfur and 1 sulfur. So I'm going to put a 1 here. I've got 4 fluorines, so that means I need a 4 in front of HF. And then if I look at the hydrogens, if I got 4 hydrogens, I have to have 2 waters. And then that gives me 2 oxygens and 2 oxygens. So it looks like 1, 2, 1, 4 balances this reaction.
So we don't need to balance the charges?
No, meaning I've given you the reaction so that you consider the charges balanced. Now, if I'm really mean on a test, I say, you know, sodium carbonate reacts with something else, and then you actually have to write the whole reaction, balance the charges, balance the reaction, and then answer all these questions. However, if you make a mistake on step 1, balancing the charges, the whole rest of the test for me is impossible to grade. So for questions like this, I tend to give you a completely balanced reaction simply because it makes my life easier to grade, and I'll ask you to complete a reaction and balance it in another part. And so we really do break it up into little parts like this.
Well, that's good.
Yeah, the first test I gave, because technically I could ask one question and encompass all of Chapter 8 and Chapter 9, basically. Meaning, you know, you'd have to write the reaction, you have to balance the reaction, you'd have to do everything else. But like I say, you mess up one step, you're pretty much screwed. And so we don't like to do it that way. So is everyone okay with the balancing? Okay, so let's figure out our limiting reactant. Someone want to tell me what we're doing? Yeah, so we're going to go from grams of reactant 1 to grams of, in this case, I'm going to choose specifically SO2 because what does the second question ask me? How many grams of SO2 I make, right? So could I convert and compare grams of hydrofluoric acid? Sure, but what's the point? And so we're going to go from grams of reactant 2 to grams of SO2. So notice that we're going to have to do more than just have a mole-to-mole ratio in our questions, because in chemistry we always measure things out in grams, unless we're doing volume, and then we'll talk about that tomorrow or Friday. And so we're going to take our 50.0 grams of SF4, and if you look on that flow chart, the very first step to go from grams to moles is simply to have a molecular weight. So here's our molecular weight. And I'm not even going to put the molecular weight in yet, mostly because I don't have it calculated. Oh, I do have it calculated, 108.07. And then the next step is always a mole-to-mole ratio. So if you're kind of looking at that Chapter 9 flowchart I handed out, you should be able to see that on the flowchart, if I start with grams of A and I'm going to grams of B, this is the path I'm taking, right? I'm first using a molecular weight, then I'm using a mole-to-mole ratio. And we know that what? 1 mole SF4 is 1 mole SO2. And then we know that 1 mole of SO2, I don't have this molecular weight calculated for some silly reason. So let's see, oxygen is 16 times 2, plus sulfur is like about 32 also if I find a chart. Where's my periodic table? Boy, I'm about to fail my own class, because I always say if you don't have your periodic table, just sulfur. It's 32.065. So we'll just say it's 64.07 grams of SO2. And we plug that in our calculator. So 50 times 64.07 divided by 108.07 is 29.64. And actually, I really should only have 3 sigs, so 29.6 grams of SO2. So notice, if I have 3 sig figs in that starting number, I better have 3 sig figs in my ending answer.
On your little chemistry paper, on your chemistry paper homework, it said always use 3 sig figs no matter what.
Yes, and the reason for that is because programming the computer to figure out and calculate sig figs was a huge extra step that I didn't feel like doing.
That's because sig figs are really unnecessary in life.
I am not going to argue with you this morning. So we've got, what, 100 grams of H2O. And so notice that we're going to do almost 90% the same thing. The only really first difference is the first step and the second step. So we know that 1 mole, I know, really it's a bunch of different stuff, so never mind. What I mean is theoretically we're doing the same thing, because we're just doing molecular weight, mole-to-mole ratio, and then a molecular weight. So 1 mole of water is 18.02 grams of H2O. And then we know that there are, what, 2 moles of H2O is 1 mole of SO2. And then we know that, so in the balanced reaction, I've got a 2 in front of H2O. Yeah, sure. We'll actually go back and we'll kind of say it again too. 64.07 grams of SO2. So it's really the very first problem. You know, we're doing a molecular weight again. We're doing a mole-to-mole ratio and a molecular weight. So if you pick up on that pattern, if you just tell yourself, 9 times out of 10, if I start in grams, I better just calculate a molecular weight. And then you tell yourself, 9 times out of 10, after I do the molecular weight, I'm going to do a mole-to-mole ratio step. You're probably right. And then 9 times out of 10, after the mole-to-mole ratio step, we do another molecular weight step. So, you know, this pattern repeats itself over and over. Cody.
So do we know to go to, I guess I'm struggling with figuring out in that whole thing, why we went to SO2.
Mostly because in step 2,
Oh, is that why?
yeah.
Is that always going to be that way?
Usually these questions come together, right? Meaning that all 4 parts are going to be there. And so if in part B I ask you to calculate grams of SO2, then convert to SO2. If in part B I say calculate grams of hydrofluoric acid, then convert it to hydrofluoric acid. As long as you're converting to the same product and comparing apples and apples, then you're okay.
So hydrofluoric acid, we're not even freaking using this.
Not in this problem.
Okay. I'm just trying to.
Unless,
grasp
you know, we
around.
could put part E, you know, how much
No, I know.
HF do we make? You know, we really can add a step, but we don't need to. Jess.
So, is it always going to tell us in B which product we're using?
Yes.
Okay.
If not, if it really doesn't tell you, and it simply says, like for instance, I got to be honest, on the homework, one of the questions is simply calculate the limiting reactant, and it doesn't tell you to do step B. In that case, you get to choose whichever product you want.
You get to just choose one. Okay.
Yep.
But I'm like, well, what if What if I choose hydrochloric acid?
You just have to do.
I'm gonna choose the
Is this what people got for the second one?
Yeah.
Okay, so Jay, what do you want to look at here?
I'm just really cool.
Okay.
Supposed to only use 36
Well, in this case, this is 4 sig figs, so this answer is allowed to have 4 sig figs.
Yeah, I saw too.
Oh, sorry, SO2, you're right.
Now, is it okay if we got a little bit?
If you
like
got-
if I got 70 or 178.1.
It just means that you typed something in your calculator strange, or I did.
I have a different molecular weight for water than you. I
Oh.
have 17.99.
It's not 17.99, so don't use that.
For water?
It is maybe if you don't have enough sig figs in your hydrogen and oxygen, but if you add enough sig figs, it should be at least 18.02. Yeah, it should be more sig figs, but well, it really depends. Like, it depends. Use the numbers in your periodic table. And really, no, I probably won't quibble over 1/10 of a gram. I really don't normally quibble over 1/10 of a gram, or 2/10 even. So, this answered A and B. So what was the answer to part A?
Part A,
That's a four.
Yeah, SF4, because it produced the least amount of SO2. And it also answers part B, which was the yield of SO2, which is 29.6 grams. So you did 2 calculations, you got 2 answers, that's fair. And so for part C, then we know that our excess reactant is SF.
Jay, can you go back? I'm so sorry.
No, that's fine.
So the yield is just the amount produced.
Yes, the theoretical yield is how much you make of something.
To use the smaller number.
Yep, because see, the idea is that as we're doing the reaction, just like in baking, we run out of SF4. Well, once we run out of one of our reactants, we can't make any more product, so we have to stop at making 29.6 grams of product, even though we have a lot of water left over.
Oh, okay.
So our excess reactant is then H2O, right? And so we want to find out how much is left over. And so here's where we take our limiting reactant and we convert it to grams of excess reactant. And so again, we're just going to start off like we kind of did, 50.0 grams of SF4. The very first step is, of course, a molecular weight to convert it to moles. And so that was, what, 108.07 grams of SF4 is 1 mole SF4. And we're going to use a mole-to-mole ratio again. And so 1 mole of SF4 is 2 moles of H2O. And then we're going to use a molecular weight again. And then, of course, the last step is molecular weight, so just 1 mole H2O is 18.02 grams of H2O. And I haven't been showing this, but I really should point it out just to be sure. Notice that to make sure you're doing things right, all your units should cancel out. And if they don't cancel out, then you're doing something wrong. You've flipped a mole-to-mole ratio or you've flipped a molecular weight. So double check by canceling your units. So let's see, some people have calculators out. Let's see if we all agree. 50 times 2 times 18.02 divided by 108.07 is 16.7 grams of H2O. And so you started with 100. You used 16.7. That means that the leftover is 100 minus 16.7. I should be able to do that in my head, but
Why are we doing 100 grams?
because we started with 100 grams of water, right? So if you go back to the original question, we started with 100 grams of water. And so that's how much we had to start, but we only used 16.7 grams of water to react with the SF4, and then we ran out of SF4, so that means that all the extra water is still sitting around in the reaction.
So the water fountain here does not work?
The water, we do not want to put any water down the drain here currently.
But if I catch it all,
If you drink from the water fountain and you don't spill any, that's fine. The idea is that currently our drain system is backed up and it was slowly draining. They're not sure if it's a clog, in which case they should be able to, you know, dump nasty chemicals or run a router through or whatever, or if it's a break in the pipe. If it's a break in the pipe, that could be serious, because that could necessitate digging up like the floor in our prep room, and that might take days or so to figure out. But we'll know more hopefully later today.
Will that mean no lab? That'll mean no lab?
No, we'll figure something out.
Dang.
Well, we shouldn't even be able to teach over here with no bathroom.
In our answer, should we write 83.3 grams of H2O left over?
Yes, 83.3 grams H2O left over. And then part D was percent yield. And so we know that we were given the experimental yield was what? I forgot already since 18 point what? 0 grams of SO2. We know that the theory, which is really just part B, was, someone help me out, 29.6 grams. So who's got a question here?
Never mind. Got it.
And so we really just take 18.0 grams divided by 29.6 grams times 100. So 18 divided by 29.6 is 60.8%.
yes, I do have a question.
Yes, Jay.
18.0 grams.
Mm-hmm.
Is that in the question?
Yeah, that was given in the question. Or that would be what we would measure in lab. Now, if you do get a percent yield over 100%, what does that mean?
You used it all up.
Means one of two things. The most likely case on a homework or a test is simply Jay made up a number. In lab, what it really means is that you have a contamination, that your product is contaminated. Because we know it's impossible to create or destroy matter, right? So if you really make more than you should, you did not just create matter, you just have something contaminating it, or made an error in a calculation or something like that. So just because my two examples in class had a percent yield less than 100%, if on a homework or a test or the website you get a percent yield over 100%, don't freak out. It just means that whatever number I randomly made up was there. I almost made up a bigger number than 18, but then I looked at it and I kind of did the math in my head and said, well, better not make it too high because then it'd be over 100%. But I should have maybe just as an example. So that's the Chapter 9 homework in a nutshell for homework 9D. And I think 9E is about molarity, right? I remember right. 9D. So yeah, 9E, what we'll do is we'll do 9E Friday. So this is due Friday. And then what we're going to do the rest of the week is questionable. So this is either going to be lecture or the lab on titrations. What I'm going to suggest for the titrations is do the pre-lab skip the last question, because we haven't talked about it yet, and so it'll be tough to do. Jess?
If we do lecture tomorrow and lab on Friday, are we just gonna have a short lab period?
Well, we have two choices. We can, technically, since we're at 8 o'clock in the morning, we could just start at 7:45 and go to 9:20, and that really does cover what a normal lab period would be. And then we could have just a short lecture, or a normal size lecture, I should say, on Thursday. I don't know if everyone wants to come in at 7:45 on Friday or not.
I was here at 7:58. Yeah, so it's.
Yeah, that's kind of my theory too. And so we'll just see how things go, okay? Well, it's pointless to worry about it until we find out more, and we'll just find out Thursday what we're doing. I mean, I don't think anyone's life is, like I said, we'll worry about it on Thursday. If it turns, because it's like saying, you know, what if the world blows up tomorrow? What should we do? Well, let's just worry about that tomorrow if the world blows up. It's probably not likely to blow up. They'll probably fix the plumbing. We'll probably just have lab and not have to worry about anything. I'm just kind of preparing you for that.
So skip the last question. I'll do that.
Right. So, what we're looking at for next week, so no class.
Woo! Yeah.
One of these 2 days, we're looking at an exam all over chapter 8 or 9. And we'll just figure out which one it is then. And Tuesday would be the second day of lab.
So review would just be
And Monday would start on lecture chapter 10. Next Friday is November 1st. We won't have class that day because I have meetings. And a certain part of me said I should put the test on that day, but then I also remember saying that, you know, having a test the day after Halloween is kind of mean, so no, we won't do it.
Next Friday is November 1st.
Okay, the other thing I want to do for a few minutes, what?
Next Friday is November 1st.
Yes.
Do we not have class for biology November 1st? I'm going home.
We'll, of course, have the extra credit test on Friday.
This Friday?
There's no extra credit, remember. So I'll put this all up on the website as soon as I get a few free minutes, which usually is not until like after my math class. Oh, the other thing is, of course, I'll put my office hours in Striegel again from 1 to 3, mostly because if we don't have bathrooms here, why be here?
It's kind of nice to be in a different building too.
Yeah, I kind of like to get out too. The only thing that sucks for me is that I have to drag my lunch over there or have to rush off and get Chinese. So
just today.
today, 1 to 3.
I might be
Just
able.
go eat in the caf.
I might be able to come over there.
Chinese is so much better tasting. I like our Chinese place here. It's not perfect because it's not very spicy, but I miss really authentic Chinese food from when I lived in DC. But yeah, I miss Burrito Express too. Real quick, for review in chapter 8, because I want to start preparing you for the test. There's 3 extra practices on the website now. Version 1 should be 100% correct, I think. Version 2 should probably be like 95% correct, meaning it's been up on the web long enough for people to catch the mistakes and for me to have remembered to fix them. Version 3 is new. So if you find something funky on version 3 in the answer key, or it looks like I copied and pasted something or something, it's extra practice.
Credit.
Practice.
When you correct you.
Oh, yes, when you find mistakes in my stuff, it is extra credit.
Yeah.
Sorry, I thought you were saying it's extra credit. No, it's extra practice. So, you know, if you do find something funky in the version 3 one, bring it to me and I'll fix it. And don't like freak out and go, oh my God, how did he balance this? Or he said this is no reaction, but it's clearly a reaction. It just means that, because I did it in my head, I didn't have the cheat sheets with me at the time. And so, you know, and frankly, people were asking me questions and, you know, I was being interrupted. And so, really, I get distracted. And then
You can tell people that's an extra credit.
the other thing I want to start focusing in on chapter 8 is you need to have a grasp of them all mixed up. And so we've got 6 types of reactions. My first question would be, can you name all 6 types? Because if you can't name all 6 types, wow, you're really just not getting the grasp of the material. You're not getting the big picture, right? So what are the 6 types of reactions?
Double displacement,
Combustion, acid-base, combination, decomposition.
In no particular order either.
acid base, and combination.
I've got combination up above.
Well, you're,
One of the things that annoys me is combination and combustion both start with COMB, so you can't even shorthand them, dang it. Now, how are you going to recognize which reaction is which? Because it's hard to figure out what to do in a reaction if you don't recognize and say, oh, I'm doing a double displacement. It's kind of like in chapter 6 on naming, where we said, hey, you got to tell if it's ionic or if it's molecular or if it's an acid in order to name. So how can I recognize a double displacement reaction? Yeah, compound plus a compound. And then how do I recognize a single displacement? Yeah, and remember, it doesn't matter what order I do it in, right? As long as one of them's the element, right? Now, how do you recognize a combination? It's
like it'll be just one
two reactants go to one product. Now here's the trick. If you only have the reactant side, you can't really tell it apart from any of the other reactions. And so I got to be honest, 99% of the time we do the reverse of this reaction, right? I'll give you the product and you have to figure out the reactants. Or I'll have to tell you it's a combination reaction. Because you can't distinguish a combination from a double displacement or a single displacement, because you always could try to mush things together. Now I have to be honest, if you really try to mush a double displacement reaction together, you're going to get something that makes no sense, because you've got 2 cations and 2 anions. We've never seen something that looked like that. Same thing with a single displacement. If you're trying to mush everything together, you end up with like 2 cations and it looks strange. And so really you kind of can tell the difference. But again, I'm not going to try to trick you, so I'm going to let you know up front, I'm either going to give you the product or tell you it's combination. Now, decomposition you can recognize. That is one reactant goes to 2 products, right? And so if you see just one thing in the question, well, I don't know how you're going to do double displacement with only one thing. I don't know how you're going to do a single displacement with only one thing. I don't know how you're going to do an acid-base reaction with only one thing. So that one really is decomposition. Acid-base should be able to be reasonably recognized. It's something with an H in it and something with an OH in it. So, you know, it really is. You just have to recognize acids and bases. And then for combustion, it's something plus O2 gas. And that something is usually carbon, hydrogen, and oxygen mixed up in some way. But really, it's just plus O2, right? So key in on those things. Recognize or try to figure out some way that you can link up each of those things in the right-hand column with what's in the left-hand column. And it's no harder to me, to a certain extent, to memorize that and to be able to even just walk into the test and write it down, if nothing else, before you start, than it should be to memorize 50 bones in a body or 50 muscles in a body or 210 whats? Yeah, see, I'm a wuss. Because, I mean, seriously, she makes you learn 210 bones.
That's our next test.
And all like the divots and different.
Right, and so
Like a process.
you find me a test where I ask you to memorize 210 things in it. Now, I have to admit, the big difference between chemistry and biology is I ask you to learn processes and remember processes, right? That is a different learning technique than just memorizing 210 things. So I mean, there is that difference there. And chemistry is more math because there's math steps involved. So recognize it, okay? That's the first thing I want you guys to do. So come back tomorrow kind of knowing this, okay? And, you know, if you want to work on that handout I gave you, the other part was what are you going to do, right? The steps to do the reaction. And then for some of them, there was what I just call something special that you had to remember. You know, like special for acid base is add plus heat. Special for combustion is add plus heat, right? Double displacements, you have to check solubility. I mean, you have to do that for all of them, but this is what tells you if there's no reaction. For single displacement, the special thing is your activity series. So there's always something a little special about each one that makes each one a tiny bit unique, which is the annoying part probably, right?
What was the che101?
For the double displacements, I know my lines are probably getting a little off.
And for like the combinations, to know the gas things, I feel like.
Yeah, no 8 common gases. I have, okay, so I'll be honest. Gosh, grading homework last night, I felt like, you know, I kept reminding people in lab, I kept reminding people when they're doing their homework. I said, remember the three decomposition reactions. The number of people that I probably took more points off for not memorizing decomposition reactions and maybe not recognizing combustion reactions, not combustion, acid-base reactions than any other thing on the test, or on the homework, I should say. So when I ask you to remember something, it's usually because I ask it a lot. Same thing with, you know, the common gases. Those will show up a lot, and so that's why I want you to recognize them. So I'm not asking you to memorize 210 bones. I'm asking you to memorize 8 stinking gases and 3 reactions. 11 things. Whatever. I don't know how many fingers I'm showing. So my moral of that story is memorize it. Okay, I think we'll end and go with questions. I just wanted to get you guys going in your studying for Chapter 8, because the key is Chapter 8 is not going to be, you know, balance this double displacement reaction. It's going to be, here's 10 reactions, go at it. Meaning they are going to be mixed up, and so you do have to practice them mixed up. Okay, so I've got 20 minutes or so to answer questions here once I hit the save button on everything and do all that.